Hello, everyone. Today I'll talk about our work on robustly learning affine transformations. This is a joint work with Pravesh Kodari, who is a assistant professor at CMU, and Santosh Vampala, who is a professor at Georgia Tech. Let's start with the definition of affine transformations. In particular, in our problem, the affine transformations of hypercubes. So affine transformations of the standard hypercubes looks like in this form. So small s is the point from the hypercube that is a uniform distribution from -1 to 1 for in d dimensions. So for each d coordinate, it is uniform between -1 and 1. And we'll apply first a matrix capital A and plus a vector small b. Then we'll get a new point. And our goal is to learn this capital A and B. Those are the annual parameters of these affine transformations. So in geometry, the affine transformations are a composition of the following. So the first type, the translation. So we can translate or shift the standard hypercube by some distance to any directions. And the second one, the scaling or diagonal scaling. So it can be composed by either scaling or diagonal scaling because we have a third operation, the rotation. So after rotation, the diagonal now is changed to other directions. So diagonal scaling, it looks like a diagonal matrix for A. So translation corresponds to this small b, this translation vector, and diagonal scaling is a diagonal matrix capital A. And the last one, rotation. Rotation, in the rotation case, we don't have the b, small b is 0, and A is a rotation matrix. So A is orthogonal. And any affine transformations can be composed into this, can be a composition of these three types of affine transformations. And in this figure, we can see all these three examples we shown are in the 2 dimension. It looks like parallelograms in 2D. And in high dimension, the affine transformation of the cube are parallel pipes. So the opposite facets of this transform cube are parallel. Now let's see what's the problem of learning affine transformations. Our samples are the IID points from the affine transformations of the standard cube. So the process will be, we first take random points from the uniform distribution over the standard hypercube. So we take each coordinate uniform from -1 to 1. And then after we get a sample from the hypercube, we'll apply the unknown transformations to those samples. So the algorithm can only see those transformed points. So the points that after transformation. In the formula we just seen, that means we can only see x, not the original sample, small s. And our goal is to learn to recover this capital A and small b. We'll output the estimated affine transformations, and it's in this form, hat capital A, S plus hat B. Now, very important thing is how can we measure our distance between the true affine transformation and our estimated one. So we'll use the total variation distance to measure the error. Total variation distance is defined as the largest possible difference between the probabilities that two probability distributions can assign to the same event. And in our case, in this special problem, because the two distributions we are compare, both of them are uniform distribution on some polytope, on some cubes. So we can also see it is related to the volume of the difference between these two cubes. We can, so in this figure, the total variation we are comparing the orange cube and the blue cube. And the total variation distance between them is either the volume of this blue shadow divided by the volume of the blue cube. So it is the parts that in the blue cube but not in the orange. Or it is the volume of the part of the orange cube but not in the blue cube divided by the orange cube. So the maximum of these two is the TV distance of these two cubes. And this problem, this learning affine transformations problem, is an important setting for independent component analysis, or ICA, because when we learn the affine transformations, we have to recover each coordinate. The cube has a natural coordinates because it's a product distribution. So we'll recover those independent components for the cube. That is exactly the ICA problem. And it can also be seen as a special case of learning intersections of half spaces or polytopes, because hypercube is a special case of polytope. Now let's see what are the previous results for this problem. One of the most common or the easiest method is the method of moments. And actually we can learn affine transformations from the first 4 moments. Let's see them in details. So it's for the first moment, or the mean of the samples, it corresponds to translation of affine transformations. So suppose in all 3 cases, the blue one is the original one, or the standard cube, and the orange one is the one after transformation. So if we can estimate the sample mean, and the sample mean will exactly be the estimated translation vector, this estimated small b. We can see from this figure. And the second moment, of covariance, we can learn scaling from the second moment. For each coordinate, we can find the scaling factor from the covariance matrix. And the last one, the fourth moment, it corresponds to the rotation operation. This needs some proof, and we'll show in the next slides what exactly the theorem is and how we can use these 4 moments to find the efficient algorithm to learn the affine transformations. So Friis, Jarrett, and Cannon, they prove that the local maximum of the 4th moments are in the directions of normal of facets if the cube is isotropic. Isotropic means that the cube has 0 mean and identity covariance. Also, we can think it as there is no shift or scaling because the 0 mean means no shift and identity covariance means there's no scaling. And now the problem is just narrowed down to how do we find the local maximum of the 4th moments. And that can be easily done. So in their paper, they gave a non-robust algorithm. We first make the distribution of the samples isotropic. So we estimate the mean and covariance of the samples. Then we can use the reverse of the transformation to make the sample isotropic. Then we find the directions of the isotropic samples that maximize the 4th moment. And those directions will correspond to the facet normals. Now we recover all the parameters we need. So this is a very good algorithm, and it seems it's already solved a long time ago, this problem. But now let's introduce a new setting, the robust setting. So this robustness, we introduce robustness because we want to see what if there is some noise in our sample. How should we do it in this case? And a robust setting in our problem, it means that there is a constant fraction epsilon of data is arbitrarily corrupted by the adversary. So note here, the adversary can arbitrarily corrupt our sample. So they can first maybe remove part of the good points and add outliers. And those outliers can be anything, whatever the adversary can do for our sample. They can first look at all the samples, and they can decide which part of points they want to remove and which part of and what kind of samples they want to add. So they can add extremos or anything they want. The only restriction for those corruption is just the fraction of the corruption should be a small but bounded by this small constant epsilon. And the main problem for our talk, so we want to estimate affine transformation so that the resulting distribution is within TV distance all of epsilon of the unknown transformation. And in this special robust setting, so we don't know that we don't have the exact accurate samples. We won't have a corrupted sample. And actually, this TV distance all of epsilon is almost the optimal error we can expect. So because the adversary can manipulate epsilon fraction of the points, so what they can do is they can just replace our sample or our cube, the true cube, by another cube that has a TV distance epsilon. So that means we can't do better than epsilon. And our goal is to recover it that within a constant times epsilon. So it's optimal up to a small constant. Now let's go back a little bit to see the history of robust learning. What can we learn robustly and efficiently? Unfortunately, most of the robust problems is not easy to solve, especially in the high dimension. For example, learning a single Gaussian robustly in high dimension is non-trivial. And even high-dimensional mean estimation needs novel methods. There are two groups. They work at the same time on this problem. One is Dark Nicholas, K. Lee, Moitran, Stewart. The other one is Lai, Raw, and Vampala. They both gave the following results. So they gave mean estimation algorithms in this robust setting for the nice distributions. So nice distribution means that they have bounded second moments and bounded fourth moments if we want to estimate covariance. And the result is they can recover the mean within error all of epsilon times square root log 1 over epsilon in polynomial time. So this is poly in M and has no dependence on dimension D. And this is also our goal. And this is the goal of any robust learning problem. We don't want the dependence on the dimension because we assume the dimension is very high, and that's too much for us. This result is very important, and we'll also use it in our algorithm as a warm start. Now we can see, because we just seen a result that can robustly estimate all the moments of distribution. Of course, hypercubes are the nice distribution, so we can robustly estimate the moments of hypercubes. So a natural idea is, so first let's see if FJK, the algorithm FJK work for the robust case. Unfortunately, the moments can be arbitrarily corrupted by a small fraction of noise. Even a single point can corrupt the moments and extremal. So FJK doesn't work. Now let's see if we use the robust moments instead of empirical moments in FJK. Does this work? So this doesn't work either, because robust estimators can only give us a poly-epsilon accuracy. And this is a lower bound due to the epsilon fractional noise. We can never go beyond of this epsilon error. And this accuracy is not enough in FJK. In FJK, if we want a TV distance that is independent with D, we have to have the accuracy of moments to be some epsilon over D squared. We can't get such accurate moments, so this doesn't work for FJK. Now let's see some very common used popular method in the robust statistics. For example, here the Kothari and Stura, they gave a robust algorithm to recover the linear transformations A hat. So here they assume that they don't care about the TV distance, they don't care about the parameter distance. So they can just use the robust mean estimation algorithm to estimate the mean and covariance that is enough to get a parameter distance good enough. So here they only try to recover the linear transformations A, or we can think it as a rotation matrix. So it's not exactly the same as a affine transformation, it's part of the affine transformation. And the result is that they can recover this A with the guarantee that each column of A hat is close to the corresponding column of A up to a poly epsilon relative error in L2 norm. And their algorithm, they use the sum of squares method. This is very popular in robust statistics. And they use this SOS and to get the robust estimators for moments based on, again, the method of moments. This is a good result in the sense of their error is independent with dimension. But it is in parameter distance. So it doesn't imply that even we have a very good estimation in parameter distance, it doesn't imply that it is good in TV distance. And we'll see in the next slides that what's the relation between the parameter distance and TV distance. But their algorithm, this algorithm is a good start for our algorithm. They can kind of recover the rotation matrix, and we can use this as a warm start, and we try to update this rotation matrix. Now let's see what's the relation between parameter distance and TV distance of parallel pipes. So we first assume A is a matrix with unit rows. So A can be a rotation matrix. Rotation matrix will have unit rows, but it can also a little bit, the rows of A can, they may be not orthogonal to each other. And H, here we can think H is standard cube, but because of invariance, the TV distance is invariant with affine transformation. So H can actually be any transform cube, any parallel pipes. So the TV distance between H and after we apply this rotation to H, it is tightly bounded by the sum of L2 norm, L2 distance between each rows AI minus EI. So EI, if we think H is the standard cube, and then we apply some affine transformation to H, that means whatever we put as in the place of A, or we will try to recover the rotation matrix will be the identity matrix. So here we compare with the A and the identity matrix. This is a L2 norm, L2 distance between each rows of A and I. And the TV distance is bounded by the sum of L2 norms. Both small c and capital C are absolute constants. So this is tight bound. And this theorem shows that the TV distance error guarantee requires a bound of the total sum of L2 errors across all rows, not the sum of squares of L2 errors. If here it is the sum of squares, that is just the Frobenius norm, but the bound is actually the sum of L2 error. There's no square. If we think the previous result we just mentioned, they can give a guarantee for each of these L2 norm as a Pauline epsilon, but we have to add them up. We have d dimension in total. So if we add d of them, we will get a d times Pauli epsilon error that is too large for the TV distance. Now let's see the moments distance and TV distance in some very simple example. And we'll see from these two examples why the method to moments is not enough. So the first example is the blue one is just the standard hypercube, and we shift it by epsilon in the diagonal directions. So we shift it by epsilon of the mean in L2 norm. Because it's the diagonal direction, that is all one direction, so in each coordinate is shifted by epsilon over square d distance. Now we can compute the overlap between these two cubes. On each side, it has a side length of 1 minus epsilon over square d. And we multiply them together to the power of d. We can see this value is almost 1 minus epsilon times square d. So the TV distance between these two cubes is around epsilon square d. It has a dependence on d. And we can see the difference distance between the moments of these two cubes. The first moment, or the mean, because this shift by epsilon, we can see their mean has a distance epsilon. And for all higher moments, higher order moments, they are the same because we don't change the shape of the cube. The only difference in the moments is the first moment. And it is only a distance of epsilon. There is no dimension, there is no d, but the TV distance has a dependence on d. So this means that even if we can perfectly learn all the higher moments, and a small error in the first moment in mean can make the TV distance very large. And let's see the second example. Even if we assume the mean is known, that we have the exactly same mean, and there's no shift. And in this example, let's see, we rotate the matrix by a small angle epsilon. Again, we can compute overlap between these two cubes and get the TV distance is almost epsilon d. So it also has a dependence on dimension d. Actually, we show that any moments of order t equals to small of log d over log d is not adequate to learn the rotation. So this log d over log d is already a very high order of moments, because if we want to estimate such a high order moments, we need exponential time to do this, to get the moments of this order. So we can't afford to have such high order. Now we know we have to get some method that's beyond moments to learn the affine transformations. Let's see this inefficient algorithm. So suppose we can find the smallest cube that containing at least 1 minus C epsilon endpoints. So those black points are our samples, and blue one is the true cube. And we find this orange cube. This is the smallest cube, the cube that has the smallest volume, and it contains at least 1 minus C epsilon endpoints, so it contains most of the points. This guarantees a C epsilon TV distance error between the blue cube and the orange cube. Of course, it takes exponential time to find such a good cube of the orange one with the smallest value and contain enough many points. But still, this can give us a good TV distance error. Why? Because we already seen that the TV distance is bounded by maximum of the volume of shadow over the volume of the cube. So either this blue shadow or the volume of the orange shadow. And we know that blue cube or the true cube has a larger volume. We always take the smallest cube that contains this number of samples. So of course, the true cube satisfies this condition. So the true cube has a larger volume, and the difference or the number of samples between in the difference of the true cube and the orange cube we find is only C epsilon n. So we have C epsilon endpoints in the shadow and endpoints in total. Then we can see the ratio between them is C epsilon. That means the TV distance is C epsilon. So this inefficient algorithm gave us a good error guarantee. Although it is inefficient, we can think it as a good goal to achieve. So our goal now is to make our cube have more points while the volume keeps the same. And this is our idea. This is the exact idea we use in our algorithm. And there's no moments in the idea. So we update the current cube to add the high density part. So we find those parts on the boundary of the cube that it contains more points, but with a relative small volume. And also at the same time, we can remove the low density part. So those parts has the size of points inside is small, but volume is large. Now we can state our main theorem. Given Y, that is epsilon corrupted sample points from an unknown parallel piped, there is a polynomial algorithm that outputs height h, the estimated parallel piped. Like it is height a times the -1 to d plus height small b. So this height a and height b are the parameters we want to learn. And our guarantee is that the TV distance between these estimated parallel piped and true parallel piped is all of epsilon. We'll deal with the 3 types of affine transformations. We introduced these 3 types at the beginning of affine transformation definition. So we divide them into 2 parts, and we'll deal with them in using 2 different algorithms. So the first one is the shift and scaling, and second one, rotation. Although we have 2 different algorithms, both of them follow the same idea. So the idea that we get from that inefficient algorithm, we'll update the current cube to add a high density part and remove the low density part. And use this, we can achieve the same goal, so to contain more points inside our cube. Both shift and scaling, rotation and rotation algorithms have the same scheme. So we checked if the current cube passed the test. If not, we'll update according to the test result. So the test result will tell us whether the current cube is good enough. So it already has a good TV distance, or it will tell us that in which direction we can improve our cube. All the tests for both shift and scaling and rotation are in low dimension. Actually, it's in 1D. So we just check the parameters and update them in 1D each time. That is, we learn the 1D parameters separately. For the mean, that means the entries in each coordinate, the entry of the mean. And for the scaling, that is the scale factor in each coordinate. For rotation, that is the phi-side direction. So we have D phi-side directions. We learn them separately. Now, we may have the question that's why we can do this in single direction. If we add them up, can the error explode? Yes, that can be the case. So there is another extra step, the filtering step, to make sure that when we add up the error from different coordinates, we don't create a dependence on the dimension. So during the filtering step, we'll remove outliers that can corrupt at least 2 coordinates. So if some outlier can corrupt 2 coordinates, we'll just remove them. We use the same filtering test in both cases. We check if there are too many points in the 2D intersection of the slabs. So in both cases, let's first see this shift and scaling figure. This is a slab on the boundary. It has a small length in this direction, and it has a full length in all other directions. So it's a very thin slice in this direction. And this is the same in the other direction. And what we count is the intersection here. It looks like a small square in 2D, and in high dimension, it has a small length in these 2 directions, but has a full length in all other directions. And we'll check if there are too many points. We should know that the correct density for these small parts, because the cube is uniform and we know all the length. If it has too many points, we just remove all of them. For example, if it have twice as many as the correct density, that means if we remove all points, that means we remove at least half of them at noise. So it's safe to remove all the points here. And same for the rotation case. We also check the intersection of all the boundary slabs. And by this step, we make sure that we can learn and update our parameters separately in 1D. So this is an important observation. Why this filtering step is enough. This lemma says that suppose we have D subsets S1, S2 to SD, and we let the fraction S equals to the size of S, the number of points in S, divided by N, the total number of points. So this is the normalized size of S. Now, suppose we have the following 2 conditions. The first one is the fraction of the union of SI is epsilon. So if we think those size are outliers, then this means the union of those outliers is bounded by epsilon. And the second condition, for any pair of ij, the fraction SI intersection Sj is upper bounded by alpha times fraction xi times fraction sj. Alpha, it can be any number that's greater than 0, such that alpha times epsilon is less than 1. So epsilon is the corruption fraction. In our algorithm or in our problem, it should be a small constant. Then alpha can be some constants that larger than 1. And we can take whatever is satisfy this condition. Now, given these two conditions, we can conclude that the sum of fraction xi is upper bounded by epsilon over 1 minus alpha epsilon. If we make sure that alpha epsilon, for example, we can make alpha epsilon equals to 1/2, then the denominator here equals to 1/2. So the right-hand side is 2 epsilon. That the conclusion is just the sum of fraction xi is bounded by 2 epsilon, by a constant epsilon. We can see this is actually the reverse of the union bound. The union bound says that we can bound the probability of union of some events by the sum of the probability of those events. And here we bound the other way, the reverse direction. We bound the sum of probabilities by the probability of the union. So the right-hand side is epsilon. Epsilon is actually the fraction of the union. This lemma is easy to prove. We can prove this by another equivalent lemma. So if we suppose y is uniform distributed on the union of xi, so I is a random variable, then we can construct random variables xi from each subset xi. Xi equals to 0 if y is not in xi, and xi equals to 1 if y is in xi. Now we can state our lemma in a different language, in the language of xi. And it's easy to see that these two lemmas are equivalent. So suppose x1 to xd are random variables on 0, 1. Then if for any ij, pair ij, the expectation of the product xi, xj is upper bounded by epsilon times the product of expectation of xi and the expectation of xj. So this condition corresponds to the second condition in the first lemma. In the first lemma, we have this bound in the fraction of union is bounded by the fraction times the fraction of xj. And here it is theta is the expectation of the product. Product is upper bounded by the product of expectations. Suppose we have this condition, then we'll get the conclusion. Similarly, the sum of expectation of xi is upper bounded by 1 over 1 minus epsilon. And the second one, we can see it's easy to prove by the Yessen's inequality. So this is the conclusion we want. Now we have a square of the left-hand side. So by Yessen's equality, the square of left-hand side is upper bounded expectation of the square of some xi. And we can expand this square of sum. And we'll get the first part, the sum of xi square, because xi are just 0, 1 variables, then equals to sum of xi. And the second part is expectation of xi times xj. And we can bound this term by this condition, this inequality, and it's bounded by the epsilon expectation xi times expectation xj. And again, we can bound those the sum of expectation xi, expectation xj by this sum of expectation xi to square. Now, after we get this, we'll see that our conclusion, the sum of expectation xi is less than or equal to 1 over 1 minus epsilon. So what's can this lemma tell us? If we think S1 to SD as outliers, or those are the outliers in each coordinate, then can affect our algorithms, make our algorithm has an error. And the sum of those fraction xi will be the total error in full dimension, because we learned them separately. So after we combine all the parameters in separate directions, after we combine them, the total error will be the sum of fraction xi. And this lemma tell us this sum is bounded by the union of them. And because those outliers is bounded by the epsilon fraction, we know this epsilon is exact corruption fraction in our problem. So we can see that the total error is bounded by a constant times epsilon. If we make sure that it satisfies this condition. And how we satisfy this condition, we use the filtering step. We can see here, there's 2D in this inequality. So that's why a 2D filtering step is enough for our algorithm. Now we can go into our two different algorithms, one for shift and scaling and the other one for rotation. How we update the parameters in 1D. So for the shift and scaling, we'll do this. We'll check if the number of points in the 1D slab at the boundary is at least half of the expected number of the true samples. So this shadow, we count number of samples here, whether it is enough many. So if not, if the number of points here is small, we move the boundary towards the center in the volume coordinates. So that means if the density here is low, we just cut this from our cube. So we do it repeatedly until we goes into the state, or we go into the cube that out boundary has high density. And for the rotation, we use the algorithm, we call it robust gradient descent. So we robustly estimate the mean of mu. Okay, so first we see the orange cube is our current cube, and the blue one is the target. So we want to improve the current height A to the facet direction, to the blue facet direction of the blue cube. Because our cube has some error, we can see this blue triangle here. Those are the points outside our cube, but it should be the true points in the true cube. And we robustly compute the mean of this blue triangle. And we'll move our height A towards the opposite of this robust mean, the tilde mu. So this acts as some gradient of the loss function. The loss function will be the how many points is outside our cube, because in this direction, how many points. And we use this mu tilde as the gradient. We move minus mu, and we move towards the minus mu direction. Now, after we get the algorithm for both shift and scaling and rotation, how we can learn affine transformation from in general. So first we get some warm start. We have the parameters that are polynomial epsilon close to the ground truth. We can get this by the algorithms I mentioned at the beginning. So we can learn the mean in the L2 norm and covariance in operator norm by the robust mean estimation algorithm. And we can also learn the rotation matrix. So the first part is the shape and scaling, and this one is the rotation matrix. We can learn the rotation matrix by the algorithm in Kodari and Stura. And they gave us some error bound in parameter distance. This is good enough as a warm start. Now we'll alternate between the shift and scaling and the rotation until the number of samples inside our cube is at least 1 minus C epsilon. And this guarantee us a C epsilon PV distance. In conclusion, we've seen that the method of moments is inadequate for robustly learning parallel pipes. So we come up with some techniques that beyond moments. For example, the filtering and the robust gradient descent. And our algorithm is a practical algorithm with fast running time. The number of samples is like D square has a dependence on D, is D square. And the running time is linear in the sample complexity. And there are also some open problems. So FJK works for any product distribution with the force moments that are different from Gaussians. So if the distribution are Gaussians, of course, we can't recover the coordinates. But if the force moments are different from Gaussians, they give algorithms to recover the product distribution. So can we do the same thing? Can we robustly learn such distributions, such product distributions? And another direction is, can we recover the polytopes? So cubes, hypercubes are a special case of hypercubes. Can we use our algorithm to recover polytopes? And the other direction is we call the least decodable algorithm. If the fraction of the corruption is large, so it's even, we can think it at more than 1/2, can we get a least decodable result? So the algorithm should output a list of hypotheses of signs order of 1 over 1 minus epsilon. That's all for my talk. Thank you for listening to my talk.